Imagine standing inside a skyscraper that's taller than most buildings in your city. Suddenly, the floor begins to move. At first, it feels almost gentle, as if someone nudged the building. But within seconds, the entire city is shaking. Cars bounce across the streets. Power lines swing violently. Glass trembles. Traffic lights sway back and forth. Some people freeze. Others run. And somewhere beneath your feet, the ground itself is moving by more than a meter. In almost every country on Earth, this would become a national disaster. Entire neighborhoods would collapse. Bridges would fail. High-rise buildings would snap apart. Thousands, perhaps tens of thousands, could die within minutes. But in one country, something completely different happens. Instead of collapsing, the skyscraper begins to dance. It bends. It sways. It moves with the earthquake instead of fighting against it. Elevators stop automatically. Gas pipelines shut themselves off. Bullet trains slam on their emergency brakes before the shaking even reaches them. Hospitals continue operating. Airports remain standing. And millions of people survive one of nature's most violent forces. That country is Japan. Japan experiences around 1,500 measurable earthquakes every single year. Some are tiny. Some are among the most powerful ever recorded in human history. Yet despite living on one of the most dangerous pieces of land on Earth, Japan has built cities capable of surviving earthquakes that would devastate almost anywhere else. But none of this happened by accident. It took more than 100 years, countless engineering breakthroughs, and painful lessons written in tragedy. This is the incredible story of how Japan built earthquake-proof cities. Japan sits at one of the most dangerous geological locations on Earth. For massive tectonic plates collide beneath the country: the Pacific Plate, the Philippine Sea Plate, the Eurasian Plate, and the North American Plate. These enormous slabs of Earth's crust are constantly pushing, pulling, sliding, and diving beneath one another. Every second, every hour, every day, the energy builds silently underground, sometimes for decades, sometimes for centuries. Then, without warning, that energy is released. The ground violently shakes. In geological terms, Japan is located directly on the Pacific Ring of Fire, a horseshoe-shaped zone responsible for nearly 90% of the world's earthquakes. For most nations, this would be an impossible place to build modern cities. Yet today, more than 120 million people live safely across Japan, including some of the world's largest metropolitan areas: Tokyo, Osaka, Yokohama, Nagoya, cities filled with skyscrapers, expressways, bullet trains, underground rail networks, and millions of homes. The obvious question is, how? Ironically, Japan wasn't always prepared for earthquakes. In fact, the turning point came from one of the worst disasters in its history. September 1st, just before noon, without warning, a magnitude 7.9 earthquake struck beneath the Kanto region. Tokyo and Yokohama became the center of unimaginable destruction. But surprisingly, the shaking itself wasn't the biggest killer. Thousands of traditional wooden homes collapsed. Cooking fires ignited. Gas lamps overturned. Within minutes, more than 100 separate fires erupted across the cities. Then nature made everything worse. A powerful typhoon offshore generated strong winds. The fires merged together, creating massive firestorms. Entire neighborhoods disappeared beneath walls of flame. People fleeing collapsing buildings suddenly found themselves trapped by fire from every direction. Roads became impassable. Water supplies failed. Emergency services were overwhelmed. By the time the disaster ended, more than 140,000 people had lost their lives. Nearly 2 million people became homeless. Large parts of Tokyo simply no longer existed. The Great Kanto Earthquake permanently changed the way Japan thought about engineering. Officials realized something critical. The earthquake itself was only part of the problem. Buildings, roads, bridges, utilities, everything needed to survive together. Protecting individual buildings wasn't enough. The entire city had to become resilient. That realization sparked one of the largest engineering transformations in modern history. Building codes became stricter. Steel began replacing wood. Concrete construction expanded. Road networks were redesigned. Fire breaks were introduced. Emergency planning became part of city design itself. But this was only the beginning, because decades later, Japan would face earthquakes far more powerful than anyone imagined possible. And engineers would discover that surviving earthquakes required something even more revolutionary. Not stronger buildings, but smarter ones. For decades, Japan kept improving. Every major earthquake revealed another weakness. Engineers studied every collapsed bridge, every cracked building, every failed foundation, and each disaster became another lesson. Then, on March 11, 2011, those lessons faced the ultimate test. At exactly 2:46 in the afternoon, the ground beneath northeastern Japan suddenly ruptured. Not for a few miles, not even for a few hundred, but along nearly 500 kilometers of the Pacific seafloor. An unimaginable amount of energy was released in just minutes. The earthquake reached a magnitude of 9.0, the most powerful earthquake ever recorded in Japan, and one of the strongest ever measured anywhere on Earth. The main shock lasted for nearly 6 minutes. Imagine standing inside a building, while the ground beneath you refuses to stop moving. Not for 10 seconds, not for 30, but for almost 6 full minutes. Across eastern Japan, office towers swayed dramatically. Ceiling lights swung like giant pendulums. Entire apartment buildings moved several feet from side to side. Roads rippled, bridges flexed, ports shifted. The island of Honshu itself moved nearly 2.4 meters closer to North America. Earth's axis shifted slightly. Even the length of a day changed by tiny fractions of a second. It was a geological event so enormous that satellites could measure Japan physically moving across the planet. And yet, something remarkable happened. Thousands of skyscrapers that many people expected to collapse remained standing. Office workers watched computers slide across desks. Books fell from shelves. Windows shook violently. But the buildings themselves survived. Not because they were stronger than the earthquake, but because engineers had finally accepted a simple truth. You cannot stop an earthquake, so don't try. Instead, move with it. That single idea changed the future of engineering forever. Most people imagine that strong buildings should remain perfectly still. That sounds logical, but during an earthquake, rigidity can become your greatest enemy. Picture holding a dry stick with both hands. Now bend it. Eventually, it snaps. Now imagine bending a fishing rod. It curves, it flexes, it absorbs the force, and when you let go, it returns to its original shape. Modern Japanese skyscrapers are designed much more like the fishing rod. Instead of resisting every movement, they're built to bend safely. The steel skeleton inside a skyscraper isn't completely rigid. Its beams and columns are carefully engineered to flex without breaking. Every joint, every connection, every bolt is designed to absorb enormous amounts of energy. As the ground moves beneath the building, the structure sways, sometimes by several feet. People inside may feel the movement. It can be unsettling, but that controlled motion prevents catastrophic failure. Engineers often compare it to bending your knees while landing from a jump. If you lock your legs completely straight, the impact travels directly into your bones. But if you bend your knees, your body absorbs the energy safely. Buildings work the same way. Flexibility saves lives. However, for truly massive earthquakes, flexible steel alone isn't enough. Engineers needed something even more advanced, a way to separate the building from the earthquake itself. One of Japan's greatest engineering breakthroughs is something called base isolation. At first, the idea sounds almost impossible. Instead of firmly attaching a building directly to its foundation, engineers place enormous rubber and steel bearings between the structure and the ground. Think about riding a bus over a speed bump. Without suspension, everyone inside would be thrown into the air. But with shock absorbers, most of the impact never reaches the passengers. Base isolation works in almost exactly the same way. When an earthquake shakes the ground, the foundation moves first. But the rubber bearings absorb much of that motion before it reaches the building above. The ground may move violently, while the structure experiences only a fraction of the force. Some isolated buildings reduce earthquake motion by more than half. Hospitals continue operating. Emergency command centers stay functional. Museums protect priceless artifacts. Data centers keep running. Instead of transferring destructive energy upward, the building simply glides gently across its isolation system. It's one of the closest things engineers have ever created to making a building float through an earthquake. Even with flexible steel frames and base isolation, there was still one problem. Very tall buildings don't simply shake. They sway, sometimes by several feet. The taller the building, the longer that motion continues. Even if the structure is completely safe, the movement can make people panic. Computers fall from desks. Elevator systems shut down. Precision equipment stops working. Engineers needed a way to calm the building itself. Their solution was surprisingly simple. Fight movement. With movement, inside many of Japan's tallest buildings are enormous devices called tune mass dampers. Imagine holding a long ruler off the edge of a table. Shake it once, and it keeps vibrating. Now place your finger gently against it. The vibration quickly disappears. A tune mass damper works on the same principle. Near the top of a skyscraper sits a gigantic steel weight, sometimes weighing hundreds of tons, sometimes suspended by massive cables, sometimes supported by hydraulic systems. When the building sways in one direction, the giant weight moves in the opposite direction. The two motions cancel each other out. Instead of allowing the building to swing wildly, the damper absorbs much of the energy. The result is dramatic. Occupants feel far less movement. Sensitive equipment remains operational. The building becomes calmer, even during major earthquakes. One of the most impressive examples is the Tokyo Skytree. Standing over 630 meters tall, it is one of the tallest structures on Earth. At its center is a massive reinforced concrete column inspired by the ancient wooden pagodas of Japan. As the outer steel tower moves during an earthquake, the central column moves differently. Together, they reduce vibration through a sophisticated damping system. Remarkably, the inspiration came from temple builders over 1,000 years ago. Ancient craftsmanship, combined with modern engineering. A perfect example of Japan's approach to innovation. But Japan's greatest defense doesn't begin inside buildings. It begins underground. The moment an earthquake starts, it creates different types of seismic waves. The fastest waves, called P waves, travel first. They're relatively weak. Most people barely notice them. But seconds later come the far more destructive S waves. These are the waves that cause violent shaking. Japan realized something extraordinary. Those few seconds between the two waves could save thousands of lives. Today, more than 1,000 highly sensitive seismic sensors are spread across the country. The instant they detect the first P waves, computers analyze the data in real time. Within fractions of a second, warnings are transmitted across Japan. Mobile phones suddenly sound an emergency alert. Television broadcasts are interrupted. Factories stop dangerous machinery. Hospitals pause delicate procedures. School children immediately take cover. And perhaps most impressively, Japan's famous Shinkansen bullet trains automatically activate their emergency braking systems before the strongest shaking even arrives. Some trains traveling at more than 300 kilometers per hour begin slowing down while passengers still have no idea an earthquake has started. Those few precious seconds often make the difference between a controlled stop and a catastrophic derailment. No technology can predict an earthquake days in advance. But Japan has learned how to react faster than the earthquake itself. Protecting individual buildings isn't enough. An entire city must survive together. That's why Japan redesigned almost every critical piece of infrastructure. Modern bridges are built with flexible bearings that allow sections to move independently. Expansion joints stretch without breaking. Massive steel restrainers prevent bridge decks from sliding off their supports. Underground water pipes include flexible connections that bend instead of snapping. Natural gas systems automatically shut off when strong shaking is detected, reducing the risk of devastating fires. Electrical grids are divided into sections, allowing damaged areas to be isolated while power continues flowing elsewhere. Hospitals are equipped with backup generators. Emergency supply warehouses are distributed throughout major cities. Public parks often serve a second purpose. Many are carefully planned emergency evacuation areas, complete with water storage, medical supplies, and temporary shelters. Even ordinary citizens play an important role. From childhood, Japanese students regularly participate in earthquake drills. Office workers practice evacuation procedures. Families prepare emergency kits. Disaster readiness isn't treated as an occasional event. It's part of everyday life. Because when the next earthquake comes, everyone already knows exactly what to do. Despite everything Japan has achieved, earthquakes remain unstoppable. The devastating tsunami following the 2011 Tohoku earthquake proved that no technology is perfect. Entire coastal communities were overwhelmed. More than 18,000 people lost their lives. It became one of the greatest tragedies in modern Japanese history. But even that disaster changed the future. Seawalls were strengthened. Evacuation routes were redesigned. Emergency communication systems improved. Entire communities were rebuilt with new knowledge. Every failure became another lesson. Every lesson became another innovation. Today, engineers from around the world travel to Japan to study its technology. The methods developed here now influence skyscrapers in California, bridges in Chile, hospitals in Turkey, and earthquake-resistant buildings across the globe. Because Japan never tried to eliminate earthquakes, it understood something far more important. Nature is stronger than humanity, but humanity can learn. It can adapt. It can innovate. And it can build cities that don't resist the forces of the earth, but move with them. Every skyscraper that bends without breaking. Every bridge that survives violent shaking. Every bullet train that stops safely. Every family that reaches shelter in time is proof of one extraordinary idea. The greatest engineering achievement isn't defeating nature. It's learning how to live with it. And perhaps that's the real reason Japan has become one of the safest places on Earth to experience one of its most dangerous natural disasters. Because in Japan, earthquakes aren't the end of the story. They're simply another challenge that engineering continues to overcome.